introduction to probability. So let us continue that. Yeah. So last time we have defined the moments. Now we will find out the moment generating function. So we know the direct method how to find out the mean and variance. Using moment generating function also we can find out the mean and variance, etc. So let x be a random variable, then the MGF moment generating function is defined as expected value of e raised to power tx. So you know that expected value of e raised to power tx, as last time notation we have, if we have a discrete type, this will be e raised to power t x px, where px is the probability mass function, and this will be integration e raised to power tx fx df if we have x is continuous. Discrete x is continuous, then we will have integration. So expanding e raised to power tx, we will get 1 plus tx plus t square x square divided by 2 factorial plus so on. Now as last time we have seen that this expectation is nothing but for example in this case we have taken the summation over x value into corresponding probability, so that we can take inside. So in the same fashion you can take the value expectation inside here. So 1 plus t expected value of x t square divided by 2 factorial expected value of x square plus so on. Okay, so now once we know this, then we can take the derivative. For example, first derivative we take, so we will get expected value of x plus t expected value of x square plus so on. After that we will put t is equal to 0. So we will get expected value of x. So we will get in the same fashion, if we take the RS derivative, put t is equal to 0, we will get expected value of x square. So therefore we can find out here the origin moments. We can find out the origin moments here. Okay, so in this fashion we can find out the origin moment, which is denoted by mu r dash. So you know that mean is nothing but this mu2 dash is the expected value of x square, and variance of x is expected value of x square minus expected value of x whole square, that last time we have discussed variance. So using that we can find out the, using moment, first we find out the moment generating function, after that we can find out the mean and variance also, and of course also other moments we can also find out. Now let us define certain discrete distributions. So what is a binomial trial? So binomial trial is basically a trial in which we have a success and a failure. Success with probability P and failure with the probability Q. Okay. So if X counts the number of successes, so X can take value 0 and 1. So probability X is equal to 1 is, let us say, P, and has success probability P, and X is equal to 0 is Q. Okay. So we will have discrete distribution. So first of all we have Bernoulli trial. Okay. Or okay. So Bernoulli trial we have. So we have only one trial in which we have a success and a failure. Probability of success is P. Probability of failure is Q, such that P plus Q is 1. So probability X counts the number of successes. So X can take value 0 and 1. So probability X is equal to 0 is Q. Probability X is equal to 1 is P. So mean here also you can easily find using the definition itself. So that will be summation X Px. So but X is, when X is 0, this is Px is Q, 0 into Q plus 1 into P. So P. Similarly, expected value of X square is also P, because this will be 0 square into Q plus 1 square into P. This will be summation X square Px. So this will be 0 into Q plus 1 square into P. So variance of X will be expected value of X square minus expected value of X whole square, which will be P minus P square, which is P into 1 minus P, which is P into Q. Okay. So you can, okay, so this is the case. So now let us define the binomial distribution. So now here we have n trials, n independent Bernoulli trials are conducted. X counts the number of success in n trials. So X can take value 0, 1 to n. Okay. So therefore, probability X is equal to X is NCX P raised to power X Q minus Q raised to power n minus X. So here we will have n independent Bernoulli trial. Okay. So X counts the number of heads, number of successes in n trials. So here X counts the number of successes. So here number of successes can be 0, 1, 2, and maximum value can take this as n. So probability X is equal to X. So a sequence in which X successes are there. So out of n, X are successes and n minus X are failure. And out of these n, X can be arranged in NCX ways. So X is 0, 1, 2 and 0 otherwise. So this is the binomial distribution. So this is X is binomial n comma P. So you can find out by direct method the mean and variance. Okay, so now let us define now the geometric distribution. So independent Bernoulli trials are conducted till we observe a success. So till we observe a success, Bernoulli trials are conducted. So X counts the number of trials to get a success. So probability X is equal to X, which is Px. So we will have first is failure, then failure. In the last we have a success. So Q. In the last we will have P. So X can be one trial to get a success, two trials to get a success. Out of X, if we get X trials to get a success, then Q raised to power X minus 1 P. So number of trials to get a success. So X can be one trial. So then this becomes P. When X is 2, then this becomes Q into P. X becomes 3, then Q square into P, and so on. 0 otherwise. Okay. So this is the geometric distribution. So X is said to be geometric with parameter as P. Okay. So one of the important property of geometric distribution is the memoryless property. So the probability that X is greater than M is probability X is greater than M plus N given X is greater than N. So for geometric distribution, this property holds. So let us see for binomial distribution. For example, if we use the direct method, for example, here we have using find out the expected value of X. So similarly, if we do, we will get expected value of X as NP and variance of X as NPQ. So let us use the moment generating function approach to find out the mean and variance of binomial distribution. So the random variable X has the probability mass function, which is NCX, P raised to power X, Q raised to power N minus X, X is 0, 1 to M, P plus Q is 1, P is between 0 to 1. Then moment generating function is expected of E raised to power Tx. So therefore this will be E raised to power Tx, NCX, P raised to power X, Q raised to power N minus X, because this is the probability mass function, E raised to power Tx into probability mass function. Okay. So therefore this will be NCX, combine these values, P E raised to power T raised to power X, Q raised to power N minus X. Now you know that this is the binomial expansion of Q plus P raised to power T raised to power N. So now if we take the derivative of this, of the moment generating function, so we will get a derivative of the MGF, then we will get N Q plus P E raised to power T raised to power N minus 1 into derivative of Q plus P e raised to power T. So which will be P e raised to power T. After that you put T is equal to 0. So what we will get? We will get N Q plus P e raised to power 0. That means Q plus P raised to power N minus 1. But that will be 1 into P e raised to power 0. So that will be NP. Similarly, expected value of x square, taking the second derivative, put t is equal to 0, we will get this value, and p into 1 plus n minus 1 into p. And variance of x will be expected value of x square minus expected value of x whole square. So that will be npq. So in this fashion, we can find out the mean and variance of the binomial distribution using the moment generating function. So using the MGF is this for the binomial distribution, and mean is this and variance is this value npq. Now in the same fashion for geometric distribution, what we have already defined, the probability mass function is q raised to power x minus 1 into p. X is 0, 1 to infinity, 0 otherwise, p plus q is 1, and the moment generating function is p e raised to power t, 1 minus q e raised to power t, and mean will be 1 by p, variance will be q by p square. So either you will find out by direct method or using the moment generating function approach. Now, important property of geometric distribution is memoryless property. So let us see the solution of this probability x is greater than m. This is can be written as summation x is from m plus 1 to infinity into probability mass function of probability x is equal to x. Because this is geometric distribution, so therefore we will have x is equal to m plus 1 to infinity p q raised to power x minus 1. So we will have p q raised to power m, because when m plus 1, then this becomes q raised to power n, plus q raised to power m plus 1 plus q raised to power m plus 2 plus so on. Therefore p q raised to power m 1 plus q square plus so on. So therefore this will be p q raised to power m into 1 divided by 1 minus q. This is the summation of this. 1 plus q square plus so on. So therefore this will be p q raised to power n upon p. So this p will cancel out. This is q raised to power m. Okay, let us see other side. This side, whether this is q raised to power m or not. So probability x raised to power m plus n given x is greater than n is probability x is greater than m plus n upon probability x is greater than n. So intersection of both of them, so therefore this will be probability x is greater than m plus n upon probability x is greater than n. But already we have calculated probability x is greater than m, so this will be q raised to power m plus n upon q raised to power n, which is q raised to power m. So in this fashion, we have shown that geometric distribution has memoryless property.
Sir, why is this property called memoryless?
Because it has forget its past basically. X is great, survived n unit of time. Given that it survived n unit of time, it will survive additional m unit of time. Is same as that of that is in behaving as a new unit. A unit which have already used for n unit of time additionally lives m unit of time will behave as a new unit. That's why it is known as the memoryless property. Okay, so now let us define the negative binomial distribution. So let independent Bernoulli trials are conducted till we have R successes. So let random variable X denotes the number of trials required to get R successes. So what is the probability mass function here? Probability X is equal to X. So last one is a success. Okay, and before that means this is X. Remaining are X minus 1. Before that, so before that, that means total should be our X successes, R successes. We should have R successes. So last one is a success. So before that, R minus 1 successes should be there, and out of X trials, so X minus R, and last one is 1. So that means total will remain X. So that means R minus 1 success is here, and X minus R failure, and last one is a success. So that means this much we require here. So that means P raised to power R minus 1 into P, that is P raised to power R, and Q raised to power X minus R, because probability of failure is Q. And out of these X minus 1, R minus 1 can be arranged in X minus 1 C R minus 1 ways, where X starts from R, R plus 1 and so on, 0 otherwise. Okay, so this is the negative binomial distribution. So X is said to be negative binomial with the parameter R comma P. So here also we can find out the mean and yes.
So why did we assume that the last one is a success?
Because we have to stop the trial, na. So independent Bernoulli trials are conducted till we get R successes. So we cannot stop till we get R successes. So last one should be success, then only we will stop. Before that, R minus 1 successes should be there. So that total of R successes are there.
Okay, sir.
So in this fashion, we will get this, and the moment generating function using the same method, expected value of e raised to power tx. This will be summation e raised to power tx into probability mass function. So we will get p e raised to power t 1 minus q e raised to power t raised to power r, and mean and variance we can find out as r upon p. Variance of x is r q upon p square. So in this fashion, we can find out for a negative binomial distribution the mean and variance. Let us take this example. Suppose we are throwing pair of dice 10 times and asking for probability of double 5. Okay, so we are throwing a pair of dice 10 times. So that is one trial. Throwing it one time, two time, 10 times. Okay, probability of getting double 5 is 1/36. 5 comma 5, because if you are throwing this in one trial, you will have 1 comma 1, 1 comma 2 comma 6 comma 6. So probability of getting double 5 is 1/36 in one trial. So x denotes the number of times getting a double 5 from rolling two dice 10 times. Okay, so x is binomial n comma p, where n is 10, p is 1/36. So required probability, that means x greater than 0. That means what is the probability of getting double 5? So x is greater than 0. That means 1 minus probability x is equal to 0, because we know that probability of a plus probability of a complement is 1. So a complement here is probability x is equal to 0, because x can take value 0, 1, 2, 3 and so on, because this is binomial distribution. Okay, so therefore this will be 1 minus nc0 p raised to power 0 q raised to power n minus I, or 10 minus 0. Okay, so therefore this is the answer here for getting probability of getting double 5 in throwing a pair of dice 10 times. So let us start with the Poisson process. So first of all, let us see what is small o notation. F is said to be small oh if limit h goes to 0, fh upon h is 0. For example, if we take x square, then we can see that limit x square upon x, x goes to 0, that is 0. So therefore fx is equal to x square is small oh. Let us say that fi is small oh, then their linear combination means, for example, I take f1 minus f2 or something like that, f1 plus 2 times f2. Okay, so ai can take any real number here. So then that is also small oh, because fi is small oh, so you will divide by h and take the limit inside. So then that also remains small oh. Linear combination is, if let us say f1 and f2 are small oh, then clearly, because their linear combination is small oh, so therefore f1 minus f2 is small oh, f1 plus f2 is small oh, minus f1 plus f2 is small oh, or any other linear combination is also small oh. Let us define Poisson process. Let events are occurring in time. NT counts the number of events occurring in the interval 0 to t. So NT is said to follow Poisson process with rate lambda. That is, NT is Poisson process if the following assumption holds: if NT has independent increments. Independent increments means events occurring in disjoint time intervals are independent. For example, events occurring in the interval A, B and CD, AB and CD occurring in disjoint time intervals. This is the time interval, then they are independent. NT has stationary increment. That is, the distribution of NT depends on the length of the interval, not where it is situated. So that means interval depends on the length of the interval. Distribution depends on the length of the interval. For example, the events occurring in the interval N2H minus NH. So this is distributed because NH is basically occurring in the interval 0 to H, and N2H means occurring in the interval 0 to 2H. So therefore, difference between them is occurring in the interval H to 2H. That means length of the interval is H. So their distribution is same. That means their CDFs are same. So if H is small, then probability NH is equal to 1 is lambda H plus small h. That means we are assuming that in a small interval of length H, either 0 event can occur, no event can occur, or 1 event can occur. And if 1 event can occur, that is proportional to the length of the interval. Okay. And to take up the real world situation, we add small h. So that means NH is equal to 1 is lambda H plus small h, and probability NH is greater than equal to 2 is approximately 0, and that we take as, to take the real world situation, we take as equal to small h. So clearly from here, if we take these two assumptions, NH is equal to 0 will be 1 minus probability NH is equal to 1 minus probability NH is greater than equal to 2. So therefore, this will be 1 minus lambda H minus OH minus OH. But we know that linear combination of small OH function is small OH. So therefore, that becomes 1 minus lambda H plus small OH, because linear combination of small OH function is small OH. Just we have seen that. So this is the definition of Poisson process. That means NT is said to be Poisson process if NT has independent increments. Independent increment means events occurring in disjoint time intervals are independent, and NT has stationary increment. That means the distribution depends on the length of the interval, not where it is situated. And if H is small, then in a very small interval, either 0 or 1 event can occur.
Sir, can you
So
please explain probability of NH greater than or equal to 2 once again?
yeah, so we are assuming that in a interval of, this is assumption basically, that in a very small interval of length H, maximum of 1 event can occur. So that means 0 or 1 event can occur. So we are assuming that NH is equal to 1 is depends on the length of the interval, that is lambda H plus some small interval, some quantity of order small h. And assuming that this is NH greater than equal to 2 is of order small h. That means that is very negligible quantity basically of order small oh. We are assuming that thing. And if this we assume this thing, then NH is equal to 0 is this much, 1 minus lambda H plus smaller OH. Is it okay?
Yes, sir.
So that is the assumption basically we are taking. Okay. So these are the assumption of the Poisson process. So under these assumptions, NT will have following distribution: e raised to power minus lambda t raised to power n upon n factorial, where n is 0, 1, 2, 3, and so on.
How do you get that expression?
Okay, so if you want, I can prove that thing. Okay, let me, because the stochastic process also we have to show this thing. So let me just solve here also. Okay, so we want to show, but proof is somewhat lengthy. Yeah. Okay, so let me take this as P and T. Okay, define this as P and T. So when h is small, so we are assuming the assumptions and proving the other part. That means that is a P and T is e raised to power minus lambda t e raised to power 0 divided by 0 factorial. So P0 t plus h. So this is a probability n t plus h. So let me denote like this: 0 to t plus h is equal to 0. This is a notation that in the from the interval 0 to t plus h. So that means 0 to t plus h t. Here 0 events occur. P0 to t plus h is equal to 0. That means here 0 events occur. And if these 0 events occur here, that means 0 events occur here and 0 events occur here. That means this is the probability that in the interval 0 to t, 0 event occur, and n t to t plus h, 0 events occur. But events are, because by the assumption 1, that means nt has independent increments. Events occurring in disjoint time intervals are independent. So events occurring and occurring here are independent. So therefore, this using the definition of independence, this is 0 and this is probability n t2 t plus h is equal to 0 because of independent increment. Nt has independent increment. Now this is the notation nt is equal to 0. So t0t, and this we can write down probability n because of the stationary increment. Distribution depends on the length of the interval. nh is equal to 0. Stationary increment assumption. But we know that this is P0h, which we have taken as by the assumption 1 minus lambda h plus small oh. You can see this assumption. When h is small, nh is equal to 0 is 1 minus lambda h plus small oh. So using that, because h is small here, okay. So therefore, this is the value. So therefore, we will get P naught t plus h minus P naught t. Let me divide by h also. I am taking this value to other side, and remaining value here is minus lambda h P naught t and dividing by h. So minus lambda h to P naught t plus something of order small oh, P naught t upon h into oh. So let me write down OH and taking, okay, so you can write down P naught T upon H, and now taking limit as H goes to 0. So this will be is minus lambda P naught T, because this is of order small oh. So therefore limit H goes to 0, OH upon H is 0. So therefore we will get minus lambda P naught T. So you know that for this differential equation, solution is given by C e raised to power minus lambda T. Okay, and also we know that in the interval of length 0, 0 events occur with probability 1. So put 0 here. So we will get, this implies that C is equal to 1. So therefore P naught T is e raised to power minus lambda T. So therefore at least we get the solution for 0. P0 T is e raised to power minus lambda T raised to power 0 divided by 0 factorial. So that means for 0 we get the answer e raised to power minus lambda T. Okay, now let us take Pn T plus H. So this is probability n 0 to T plus H is equal to n. Okay, so okay, let me take okay, so let me take here Pn Pn plus 1. Okay, so okay, so let me take here this value as 0 to T plus H and n events here total. So n can occur here, 0 can occur here, or n minus 1 can occur here, and 1 can occur here. Because in an interval of length small oh, in interval of length h, where h is small, either 0 and 1 event can occur. Okay, so therefore this will be probability n 0 to T is equal to n intersection n T to T plus H is equal to 0, or n 0 to T is n minus 1 intersection T2 T plus H is equal to 1. Okay, so this or this. So because either this can happen or this can happen, so both of them are mutually exclusive, nothing is common, so we can write down them as separately. Probability of this plus probability of this. And again, using the same concept, stationary and independent increments, what we will get? We will get P and T into P not H, this value, plus this value, P using stationary and independent increments, Pn minus 1 T, P1 H. So therefore we will get, is it all right with everybody? Yes, is it okay till here?
Yes, sir.
Okay, so now this will be P and T, P naught H. P naught H means 1 minus lambda T plus small o h by the assumption. So 1 minus lambda plus small o h. Okay, and plus Pn minus 1t into P1t. P1t is lambda h plus small o h. So from here we will get Pn T plus H minus Pnt, this quantity, divided by H. Okay. And therefore, what we will get, this remaining quantity is minus lambda H Pnt, this quantity, minus Pn minus 1t upon H. H and H will cancel out. And some quantity of order small oh, something multiple with OH. But we are dividing by H and trying to take limit. So therefore that quantity will basically go to 0. So whatever quantity that is, that quantity, if I take H goes to 0, then that quantity will go to 0. So that's why I'm not writing that quantity, only OH upon H I'm writing. So taking H goes to 0, this becomes d Pnt upon dt is minus lambda Pnt minus Pn minus 1t. Okay. Now this is equation. Also we have P naught t is e raised to power minus lambda t, that already we have shown. So now we assume that Pn Pn minus 1t is basically is e raised to power minus lambda t. Um, Lambda t raised to power n minus 1 upon n minus 1 factorial. Okay, so we assume this thing and try to show for P and T using mathematical induction. So what we will get? So because one thing is there, we have already shown, we are assuming this thing and we are trying to show for P and T. So therefore we will get dP and T upon dt from this equation is minus lambda P and T plus lambda e raised to power minus lambda t raised to power n minus 1 upon n minus 1 factorial. So multiply with e raised to power lambda t, e raised to power lambda t, dP and T upon dt plus lambda e raised to power lambda t, P and T, this quantity, and we are left with lambda n Tn minus 1 upon n minus 1 factorial. So this is the derivative of e raised to power lambda t P and T, because this is e raised to power lambda t derivative of P and T plus P and T into derivative of e raised to power lambda t. This will be lambda n upon n minus 1 factorial into this. So e raised to power, taking integration on both sides, e raised to power lambda t P and T, this will be lambda n upon Tn upon n factorial plus some constant of integration that you adjust like that we have adjusted previously, plus c for example. So using that, so you adjust that, so we will get that will be 0. So P and T is e raised to power minus lambda t raised to power n upon n factorial. N is 0, 1, 2, so on, because using mathematical induction we have shown. So therefore this holds for all values of n. Okay, so I think the proof is done now using mathematical induction. Okay,
Sir, how are we assuming that thing? Pn minus 1t.
mathematical induction. Yeah, what you are saying?
Sir, how we are assuming that thing? Pn minus
What?
1t.
That is using mathematical induction, na? In mathematical induction, you have to you assume, you have first of all some condition is given that this is true for this. After that, you assume for Pn minus 1 and you try to show for Pn. So using mathematical induction, you prove that thing.
No, sir, we only know P0t is e raised to minus lambda t. From
Yeah,
that we
you
are
know
assuming.
that thing, na? So using mathematical induction, you just read mathematical induction that we assume for some quantity we have to show. Then we assume for, we first of all know this thing. We know this thing. After that, we
Yes.
assume for Pn minus 1, for particular quantity we assume. And for P and T, if we show that thing, then we are done. Using mathematical induction, that is basically proved.
Sir, I am saying that how exactly we are assuming that thing only. Like
Yeah, you just
that Pn.
see, you, I think you have done mathematics 1, you have done mathematics 1 and 2. Yeah,
Yes.
just read that. Yeah, you just read that. That is using mathematical induction. So you just use mathematical induction here. Okay.
Okay.
We assume for P0T, and we first of all we have to show for one quantity, then we assume for this, then we assume for PNT, so that we are done basically. Okay, let us stop here.